All right, everyone, welcome back to Conceptual Physics Projectile Motion Zero Launch Angle. So, projectiles that are launched with a zero launch angle are launched completely horizontally. These projectiles don't have any velocity in the y direction initially. So, what that means is they're going to be launched out horizontally, something like this, some kind of projectile, and it's going to be falling like this. So, at the very beginning, it's going to have a velocity in the x direction, but at the very beginning, it's not going to have any kind of velocity in the y direction. Velocity in the y is just zero. Okay, let's see some examples of this. It'll make more sense with examples. But first, refresher of equations. So projectile motion has motion happening in two dimensions simultaneously. To solve for problems that are in 2D, we need to break up the components into x and y components. Okay, and solve from them there. Solve from there. So luckily, in the x component, since there is no acceleration, velocity in the x direction is constant, we only use one equation. So we only have one equation in the x direction because there's no acceleration. In the y direction, however, there is acceleration, there is gravity. There is acceleration in the y direction, so we use a couple of equations. We have the original equation. Acceleration in the y is equal to v final in the y minus v initial in the y divided by t. And then we have this one that we learned from free fall. Displacement in the y is equal to 1/2 ayt squared. And reminder, this displacement equation, you can only use this when the initial velocity in the y is equal to 0. Okay, you can't use that when it's not that. So these are the equations. Just also another refresher, all these equations we've learned from 1D kinematics, but if you want to manipulate them to find different variables, I have them all written down over here. So if you want to copy them or whatever, you can do that. But you can solve all these manipulated variables with algebra, but if that is something that is difficult, I suggest either memorizing them or writing this down. Great. Now let's move on. A ball rolls off a table moving 10 meters per second. The moment it leaves the table, how fast is it moving in the x direction and in the y direction? So this ball is going to be rolling off. Oops, that's kind of looking like it's going at an angle, and this is 0 angle, so let's change that. This ball is going to be rolling off, going 10 meters per second. Okay? So what we should know is when it rolls off, the moment it rolls off, it's going to be going 10 meters per second in the x, but what we should know in the y direction is it's going to start in the y direction with the initial velocity of 0 because it's just rolling off completely horizontally. And that's a key thing to know with all these examples with zero angles or things that are launched horizontally. The initial velocity almost always is 0 while it has an initial velocity in the x direction. Okay, so in the x, 10 meters per second, in the y is 0. A ball rolls off the table, moving 10 meters per second across the table. After the ball has been in the air for 1 second, what is the velocity of the ball in the x direction? B, what is the velocity of the ball in the y direction? And C, what is the speed of the ball? Okay, very similar thing here. Okay, this thing is rolling off. Actually, I'm going to draw that smaller. It doesn't matter too much, but I'm just going to do it smaller. Okay, so let's say 10 meters per second. Okay. So 1 second, whatever second, all throughout the motion here, this ball is going to be going 10 meters per second in the x direction. So it doesn't matter at the very beginning, at the very end, it's 10 meters per second. And any time in between. So this is just going to be 10 meters per second in the x direction. What we talked about in the y direction at the very beginning when it rolls off the table, it's going to be 0. However, what we should know is in the y direction, it's going to be getting faster and faster and faster and faster, and that is because of gravity. So after 1 second, let's think about how fast it's going to go. So we should know that the acceleration in the y is equal to negative 10 meters per second squared because of gravity. So that means every 1 second, the velocity is changing by 10. So it's going to go from 0 to negative 10 meters per second. And if we did this mathematically, we should be able to see this. So we should know the final velocity in the y is equal to the initial velocity in the y plus acceleration in the y times time. Maybe before I show that, where did I get that equation? Let's go back. I got it right here. So I derived it did some algebra from this equation here, and I manipulated it right here to get that. Okay, let's go back. So what I can say is at the very beginning, the initial velocity in the y is 0, because that's what it starts out with here, plus the acceleration y, which is gravity, negative 10 meters per second squared, and after 1 second, because it says 1 second. So and this is going to be equal to negative 10 meters per second. Okay, so that's how I did it both conceptually and mathematically here. Okay, so what is the speed of the ball after 1 second in the air? So, what we should know is going to be going 10 meters per second in the x and 10 meters per second in the y. And the speed here, we can use the quadratic formula. Pretty much a squared plus b squared equals c squared. I'm not going to go into all that, but I'm just going to be doing square root of 10 squared plus 10 squared. And let me put that into my calculator. Get 14.14 meters per second. And again, we don't need a direction or anything because it asks for speed. And we don't need negative or anything because it asks for speed. Okay, great. Okay, let's look at this example. A ball rolls off a table moving 10 meters per second. If it takes 0.4 seconds to hit the ground, with what speed does the ball hit the ground? How high is the table off the ground? Okay, so this ball here is going to be rolling off the table at 10 meters per second. Okay, how should I do this? Okay, I think I'm gonna start implementing the strategy. Let me just call this A and B, part A and B. I'm just gonna start implementing a strategy that we're pretty much just gonna always use for projectile motion problems. So, and how that's gonna start out with is we want to break down everything into x and y components. So we should know in the x direction, the acceleration in the x is always going to start out with 0. Why is that? Because the velocity in the x is constant, meaning it's not speeding up or slowing down, so the acceleration in x is always 0. Acceleration in the y is going to be negative 10 meters per second squared because that's gravity. Gravity is pulling down around 10 meters per second squared. And I always like to, when I'm breaking things down into components, I like to start out with acceleration because they're almost always the same. X is 0, y is negative 10. Okay, next, what do we know? Let's think about the velocity in the x. It's going to be rolling off this table at 10 meters per second. And we should know with the zero angle problem, when things are rolling off horizontally, the initial velocity in the y is always 0. Okay, I shouldn't say always, almost always 0. Okay, pretty much you're always going to see a 0 in high school physics. And then what we should know, we learned about this before, is time is the only thing that's going to be the same in both the x, 0.4 seconds, and in the y, 0.4 seconds. So that's the only one that's going to be the same in the both. So with what speed does the ball hit the ground? And we should know the x. The x is always the same. It's going to be hitting the ground at 10 meters per second. The velocity final in the x, I guess I could say, is equal to 10 meters per second. However, in the y direction, that's when it becomes confusing. We don't know what this final velocity in the y is equal to. But we can figure that out. So I guess I will make this part A. Okay, part A. And we have this from the manipulated formula. Velocity final in the y is equal to v initial y plus acceleration in y times t. V initial in the y is 0 plus acceleration in the y is negative 10 times time is 0.4. And it's going to be equal to negative 4 meters per second. Okay, so when it hits the ground in the y direction, it's going to be going, it's going to have a velocity of negative 4 meters per second. So now let's just combine this to find what the speed is. Because when it asks for the speed, it's not saying what's the speed in the x or what's the speed in the y. It's asking for what the general speed is, which is something we have to combine. So we have 10 going in the x direction, and we have 4 going down. And I'm going to combine this to find what the speed is. And again, this is Pythagorean theorem. Square root of 10 squared plus 4 squared. Let me figure that out in the calculator. You get 10.77 meters per second. Okay. All right, let me change colors for part B. Okay, so that was part A. Now let's do part B. Part B says, how high is the table off the ground? So we're looking for how high this table is off the ground. Another variable for that is we're looking for what the displacement in the y direction is. Okay, so we're finding what this displacement in the y direction is, and we have a formula for that. 1/2 acceleration in the y times time squared. And what we should know is when we're trying to find something in, let's say, in the y direction, we can only use the components in the y side. We can't use anything in the x except, I guess, the time, because that's the same for both. But if we're trying to find something in x, we can only use the stuff in the x. But in this case, we're looking for something in the y, so we can only be using stuff in the y. So the displacement in the y is equal to 1/2 acceleration of y, which is -10, time, which is 0.4 squared. Let's plug that all in. 0.4 squared. We get negative 0.8. But it's just looking for how high it is, so we don't need to include negative. So we can just say 0.8 meters. Okay, hope that makes sense. All right, so going to continue doing zero angle, but this next part of the PowerPoint kind of comes along with a few more stories. So, Adventures of Rolyna. Rolyna over here is a cave woman in the land of Tilapia. Recently, Rolyna's cave family was killed by a ferocious one-eyed lion. Here we go. This left Rolyna filled with a mix of rage and sadness, which caused her to spend most of her time in the mountains looking for the one-eyed lion and wandering aimlessly. All right, first question here. Rolyna is practicing her javelin throw. She throws a spear horizontally, keyword here. Horizontally kind of shows that this is a zero angle problem. At 30 meters per second towards a bullseye directly in front of her. The spear takes 0.28 seconds to reach the target. How far is the target from her? Okay, she throws the spear 30 meters per second. When it hits this target here, it's going to have taken 0.28 seconds. And right now, we're just looking for how far is this target from her. So what we're looking for essentially is this displacement in x. All right, so first let's figure out what we know in this equation, or not this equation, this problem. Again, we're starting out with everything we know in the x and y direction. And like I mentioned, we want to start out with acceleration because that's the simplest. Acceleration in the x is 0, acceleration in the y is -10. It's almost always just going to be like that. The velocity in the x, again, is thrown horizontally, keyword here. So that's going to be at 30 meters per second. So we have 30. And again, since it's horizontal, that just gives us a cue. Okay, initial velocity in the y, 0. We know the spear takes 2.28 seconds to reach the target. So time we know is the only thing that's the same in both. Great. And what we're looking for, part A is looking for, is this displacement in the x direction. How far is this target? Luckily, we have these 3 pieces of information. And when we have 3 pieces of information, we can find the fourth. So let's do that. Part A. The only equation we have for the x direction is velocity in the x is equal to displacement in the x divided by time. And now we're going to manipulate this to find displacement. Displacement in the x is equal to velocity in the x times time. Velocity in the x is 30. Time is 0.28. And let's do this. 30 times 0.28. 8.4 meters. Okay. All right. Part B. By how much does she miss the bullseye when the spear hits the target? Okay, so we should know, even though she's aiming directly at the bullseye, what's going to be happening is as she throws it, it's going to be going towards the bullseye, but it's going to slowly, or it's going to start going down. It's going to go lower. So even though she's aiming at the bullseye here, it's not going to hit the bullseye because gravity is going to be pulling it down. Okay? And what is this variable? That's going to be what we're looking for, how much it misses by. That's going to be the displacement in the y direction. So we're looking for what this displacement in the y is. And again, we have 3 pieces of information, so that should be able to help us. We have the equation, displacement in the y is equal to 1/2 acceleration y times time squared. And remember, we can only use this when the initial velocity in the y is 0, which it is in this situation. Acceleration y negative 10 times 0.28 squared. And let's put this into our calculator. And we get negative 0.392 meters. But it just says how much does she miss the bullseye, so we don't need a negative there. We could just say 0.392 meters. Okay? All right. When Rolyna meets the one-eyed lion, she realizes that she cannot aim directly at it because of a magical spirit that pulls everything downward. All right. Moving on. A one-eyed lion is out playing with his cubs. The lion decides to horizontally run off a 10-meter cliff with a speed of 12 meters per second into some water. At the same time, keyword at the same time, one of the cubs decides to follow horizontally running off the same cliff with a speed of 4 meters per second. Which one hits the water first? Okay, we already did a problem like this, so hopefully you know, but also I'm doing this again just because a lot of times people forget. So this lion over here is going off this cliff horizontally at 10 meters per second. So it's going to go something like this. And this cub gets off the cliff also flying horizontally at the same exact time, but only going at 4 meters per second. And we want to know which one is going to be hitting the water first, the cub or the lion. They both leave at the same time, but one goes faster. And we should know both will hit the water at the same time. And why should we know that? Because they're both going to be falling off the cliff with the same distance in the y direction. Gravity is what's going to be pulling them down, and that's only acting in the y direction. So gravity is going to be pulling them down the same distance in the y direction, even though the line is going faster in the x direction. Okay, the x doesn't affect the y. Okay. Very similar question here, but very similar prompt, but different question. A one-eyed lion is out playing with his cubs. The lion decides to horizontally run off a cliff, 10-meter cliff, with a speed of 12 meters per second into some water. At the same time, one of the cubs decides to follow horizontally, running off the same cliff with a speed of 4 meters per second, same time. Which one hits the water further from the base of the cliff? So you might be thinking, okay, they're both going to hit the water at the same time, like the last one. But no, that's not what it's asking. It says, which one goes further from the base of the cliff? Okay. And you might be thinking, well, they're both going to hit the water at the same time. So if they're going to be hitting the water at the same time, aren't they going to be the same distance away from the cliff? And maybe that's okay thinking. But what we should know is since the lion is going faster horizontally, it's going to be going much further out, while the cub isn't going that fast horizontally, so it won't go as far out. So the lion is going much faster. So since the lion's going much faster, even though it hits the water at the same time, it'll be much further from the cliff than the cub. Okay. Next example. Rolyna finds the one-eyed lion. And starts to sneak up on it. The lion notices Rolyna and starts to dash away. Rolyna throws her spear and impales the lion. Having no choice, the lion runs off the cliff with a horizontal velocity of 8.6 meters per second. He falls into a lake 20 meters below. How much time will it take the lion to fall from the edge of the cliff to the surface of the water? Okay, let's see. Again, when we're doing these mathematical problems, we want to start out with everything we know in the x and y components. And I always, like I mentioned before, I always like to start out with the acceleration because it's almost always the same. Acceleration x is 0, acceleration y negative 10. The velocity in the x is going to be running off horizontally, and that should cue us that this velocity is all in the x direction, 8.6. And that should also cue us that initial velocity in the y, since it's going horizontally off, is in the y, the vertical direction, it starts off with 0. Another piece of information we find, it falls into a lake 20 meters below. So this is 20. And that means the displacement in the y is equal to 20 meters. So we're looking for how much time. I'm going to put that here, time. And the good thing is, at least in the y direction, we have 3 pieces of information. So that should help us find time. So let's do some calculations for that. Okay, so what piece of information do we know? So with the variables that we have this formula that we could use. Displacement in the y is equal to 1/2 acceleration y times squared. We're looking for time, so we're going to manipulate this a little bit. Time is equal to square root of 2 times displacement in the y divided by acceleration in the y. 2 times displacement in the y. Oh, sorry. This displacement should be negative 20 because he's going to be falling down 20 meters. So it's going to be negative 20 divided by acceleration of y, which is negative 10. I'm going to put that into my calculator. And that's going to be equal to 2 seconds. Okay. Let's look at part B. Part B says, how far from the base of cliff will he strike the surface of the water? Okay, so let's think about that first. So he's going to be falling like this. And we want to know how far from the base of the cliff will he be. What that is the displacement in the x. Okay. And we should know in the x direction, again, since it's asking for something in the x, we can only use the piece of information x. We only have one formula. Velocity in the x is equal to displacement in the x divided by time. And we're looking for displacement, so let's manipulate this. Displacement in the x is equal to velocity in the x times the time. Velocity in the x is equal to 8.6. And time, it doesn't seem like we have that. But remember, we found that last time, 2 seconds. And remember, time is the only thing that's the same in both of them. So we have 2 here. And that's going to be equal to 17.2 meters. Great. Last part. Let's use this. Okay. Part C says, what is his landing speed? So when he hits the water here, we should know that the velocity in the x direction is always the same. It's going to be 8.6. However, in the y direction, he's going to be going faster and faster. So first, let's figure out what that velocity is in the y direction. So final velocity in the y. So I'm going to be using the equation final velocity in the y is equal to initial velocity in the y plus acceleration in the y times time. And that's 0 plus acceleration in the y, which is negative 10 times time, 2. So this is equal to negative 20 meters per second. Okay, so you could have maybe done that conceptually. But now let's do this. Now let's combine it. So again, when it's asking for the landing speed, it's not asking for what's the velocity he hits the water with in the x direction or the y. It's asking for the combined direction. Like if somebody jumps off a cliff, into water, and we're asking for the landing speed, you're not just going to give them the velocity in the x or the velocity in the y. They want like the combined velocity. So that's what we're going to do here. We know that the velocity in the x when he hits the water is going to be 8.6, and the velocity in the y is going to be negative 20 there. And this is the speed. So speed is equal to, we're doing Pythagorean theorem here, 20 squared plus 8.6 squared and the square root of that. So let's do that. 20 squared plus 8.6 squared. And we get 21.77 meters per second. Okay. All right. Let's see what happens. Rolyna does not notice the line resurfacing from the water. However, on her way back home, she notices 3 baby lion cubs, each with one eye that has not opened yet. Okay. Let's keep going. Next example. Rolyna climbs to the top of a mountain and decides to pay tribute to her god Rogar. To make an offering, Rolyna finds the prettiest rock on the mountain ledge 40 meters above the ground and throws it horizontally with a speed of 14 meters per second. How far from the base of the cliff does the rock hit the ground? Okay. So again, we're always starting out with what do we know in the x direction? What do we know in the y direction? So again, we should know that the acceleration in the x direction. Oh, we try to do the acceleration first. Acceleration x is 0. It's a constant velocity all the time. Acceleration of y is -10 because of gravity. It's being thrown horizontally. That should cue us for the initial velocity in the y is just 0. And it's thrown horizontally with a speed of 14 meters per second. So the velocity in the x is 14 meters per second. We should know that this rock is going to be falling 40 meters. So what this means is the displacement in the y is equal to -40 meters. Okay, it says how far from the base of the cliff does the rock hit the ground? So what we're looking for is this right here, which is the displacement in the x. However, when we're looking for this, you might notice a problem. And the problem is we only have two pieces of information in the x. Something that's good is that we have three pieces of information in the y direction. So can we use that to help us with the x? And the answer is yes. If we can find time in the y, that will be the same as the time in the x. So that's what we're going to do. Looking at these variables, we should notice that we can use this formula. Displacement in the y is equal to 1/2 ayt squared. And we have, and now we're looking for time. So time is equal to square root of 2 times displacement in the y divided by acceleration in the y. So time is equal to 2 times -40 divided by acceleration in the y, which is -10. And we should know time is equal to 2.83. 2.83 seconds. And now we have some more information. 2.83 seconds, 2.83 seconds. And in the x direction, we have three pieces of information. Luckily, in the x direction, we only have one formula. Velocity in the x equals displacement in the x divided by time. Oops. So now we can manipulate this a little bit to help us. Displacement in the x is equal to velocity in the x times the time. Velocity in the x is 14. Time is 2.83. And let's figure that out. 14 times 2.83. 39.62 meters. All right. Roga was sleeping, did not notice the offering, sadly. All right, next example here. An airplane pilot is moving with a constant velocity and drops a package. In the absence of air resistance, where is the package relative to the airplane at the moment it hits the ground? Behind the airplane, in front of the airplane, directly below the airplane, cannot be determined without knowing how high the plane is, cannot be determined without knowing the distance traveled by the airplane. Okay, so this is a very similar problem to what we did at the very beginning of the chapter, but it's a little, I guess it looks a little different. So we have this plane here, okay? It's going to drop this package. And sometime in the future, this plane is over here, and it's going with constant velocity. But where is this package going to be? Is it going to be over here? It's going to be over here, or is it going to be over here? And what we should know is when this package gets dropped, this plane is going with a certain velocity. But when it gets dropped, this package is also going to be going with that same velocity. So it's going to be moving like this while that plane is moving. So what that means is when the pilot looks down, it should be directly below it. Because again, there's no acceleration in the x direction. So it's not going to be speeding up in the x direction. It's not going to be slowing down in the x direction. So it should have that same speed in the x direction when it hits the ground like this. And it should be directly below it. Okay? Hope that makes sense. If not, watch kind of like the earlier videos where it does a problem like this, where a person throws a ball straight up into the air while he's driving and it lands right where the person threw it. Okay, great guys. We've been doing zero angle for this part of the chapter, but next time we're going to be talking about angled launches. See you for that one. Bye. Thanks for watching.